So where is LiDAR used in hydrological applications? Actually, I'll just open all of these up. I think in terms of terrain attributes, land cover model inputs and monitoring, these are three areas where we can use LiDAR. Okay, that's the important distinction I want to make. These are areas where we can use LiDAR. It doesn't necessarily mean they are used in any operational way. Utilizing high-resolution DEM data for watershed delineation is a very standard procedure. It's decades-old application area now. Floodplain cross-sections, again, standard application. Drainage vectors, channel dimensions. Well, the channel dimension one is, I think, an emerging application for LiDAR. We'll look at that in a little while. Land cover model inputs, so essentially for hydrological modeling. So beyond the watershed attributes and the channel attributes, or the geometric attributes of the landscape, how can we use LiDAR in hydrological models? Well, many models need us to parameterize the hydrological response of landscape units. We typically adopt some kind of hydrological response unit approach. Whether or not they're called HRUs is another matter. There are different ways to aggregate data within a watershed. But some of those characteristics relate to the things like terrain roughness or vegetation roughness, or the ability of sunlight to make it to the ground. If there's a canopy, like how much radiation will make it to ground surface, how much rainfall will be intercepted and or is available for evaporation. And these components in a hydrological balance can be modeled from attributes like leaf area index or canopy cover. And we can do a reasonably good job of extracting those landscape parameters from a point cloud. And other attributes like permeability and roughness have been modeled from LiDAR and used as hydrological model inputs. Monitoring is probably the one area where there's a lot of potential. And at the end of this presentation, I've got some examples of where we've utilized LiDAR for monitoring in a water resources context. The one where there has been some traction in recent years is snow depth. We first did a proof of concept of LiDAR snow depth mapping in the 2001 to be precise, but we've been testing it from 1998. We did our first successful test in 2001, published it in 2004, then we did some more testing here in Alberta in 2008. But in all of that time, it's never been operational. However, in the state of California, or upstream of San Francisco, JPL are now operationally monitoring snow utilizing LiDAR. So I think that's actually kind of cool. It is actually being used operationally now for snowpack monitoring. I think we could do the same thing in Alberta. Let's look at some watershed modeling applications. Many of you that are familiar with GIS and familiar with watershed applications have seen this workflow and know exactly what it is. We start with a DEM, we fill sinks, we run flow direction, flow accumulation, we generate a watershed extent, and then we do some kind of stream order analyses. It's a standard GIS watershed workflow. And of course we can implement that workflow with LiDAR. I think many of you may be familiar with the GIS procedures involved. I don't want to dwell too much on that, but of course fill sinks is just raising the depressions in the landscape up to the lowest surrounding point so that we don't have pits in our data. Flow direction allows us to generate our flow vectors. Flow accumulation is the number of upstream grid nodes that contribute to any point on our DEM surface. And so those are standard GIS tasks. But if we're going to apply these to LiDAR data, we're dealing with high resolution, and we're typically dealing with a data set that contains information that cannot be handled readily within these fairly straightforward procedures. And to illustrate that point, here we see a highway crossing. We've got a river here, we've got a highway crossing here. At this resolution, that highway crossing creates a dam or a barrier to flow. Now if we just run fill sinks, what's going to happen is this upstream depression, this channel, will just be filled up. Now it'll create probably a hydrologically reasonable map, but the channel locations will be in probably the wrong location. Tributaries will be mapped in the wrong location. The topology of that watershed will be incorrect. So we can't just run a standard watershed analysis workflow on a high-resolution LiDAR DEM. That's maybe a bad thing, because that means, oh, we've actually got to do a lot more data prep in order to make the DEM work in this procedure. And so what that means usually is that we'll start off with some idea of what the river network looks like. Sometimes we can take aerial imagery or high-resolution satellite imagery, transpose it onto our LiDAR DEM, and we'll manually see where the streams are, and we'll identify if there are any flow obstructions, just visually identify them, and then apply some kind of burning in to the DEM so that we can recreate that or kind of remove that barrier from flow so that the other automated watershed tools will work. That can be a very time-consuming process, and there's only so much automation you can do with that. There are some things you can do, there are some algorithms out there that automate this, but I think it's safe to say that there is no algorithm out there that can truly automate all of this. Some manual intervention is usually required in this step. I did want to illustrate how if you go to the provincial databases, because this is usually where they reside, and extract provincial watershed layers, and then you recreate a watershed using higher resolution data, you'll very often find slight discrepancies between them. But I think another thing that's kind of worth noting is that in urban environments, the watersheds that we might obtain from our database, say the provincial one that we have illustrated here, is going to be the surface watershed. When we look at a data set at this resolution, we'll see that this natural watershed actually covers an urban area as well as a rural area in this particular example. When we look at it much more closely and apply the LiDAR drainage vectors and transpose the urban drainage infrastructure, what we find is that the true watershed is actually over here. And we can see that illustrated here. So there is a discrepancy between the surface drainage and the anthropogenic drainage. And I think that needs to be borne in mind. This is not a specific LiDAR application because you need extra information. Beyond the LiDAR, you also need to have some map of the drainage infrastructure. But if you put those two high-resolution data sets together, you can get a much better estimation of the true watershed rather than the natural surface watershed. That's important if you're doing things like hydrological yield calculation. You know, you stick a rain gauge in the middle of your watershed, you see what the depth of rain collection is there, and then you map that out over the entire area of the watershed. Well, if you know that your watershed is, the natural watershed is 10 kilometers, then you can calculate a specific yield. You can relate that to runoff at your gauge endpoint, and then you've got a relationship between the two. But the problem is, if you've actually got this kind of thing going on, your natural watershed may not be the correct, may not represent the true area of water collection that is actually being routed to the basin outlet. And so you need to be able to do this kind of analysis to check what the true watershed area is. And I mean, it can be very different. It could go from 10 kilometers squared down to something like 6 or 7 as a result of artificial drainage. And yeah, so in this case we can see the difference in these two watersheds is actually 12% as a result of the effects I've just described. Here, this is just, I've got a few case studies interspersed throughout this presentation. So this is one case that a student of mine worked on a few years ago. We were working with the city of Halifax, or Halifax Regional Municipality. They were putting a new highway in across this watershed area. And they wanted to know two things. How would the new highway impact the impervious surface within that watershed? And also, how many zero order or first order stream crossings would there be? Well, zero order, because first order was already mapped. How many zero order stream crossings would there be for this new highway development? And I mean, to go out into the field and map that would be very difficult. Even if you could do it, it would be challenging and costly to do it. So here's the, I'm sorry, that probably doesn't come out very well, The red line illustrates the proposed highway alignment, and then you can see in the coloured river reaches here are stream order analysis, and so we can see the zero order crossings. Well, you can kind of see them. Anyway, the point is we can map and quantify where those crossings are, and those tell us the potential culvert locations for that new highway development. And or, you know, should we put a culvert there, or should we just route it down and collect multiple crossings and route them to one crossing? And it becomes a very easy analysis if we have the high resolution DEM available to us. If we have to do it in the field, it's not such an easy analysis. And then the other element was the changes to impervious surface. Well, in this case it was a very small change, but nonetheless it was something you could very easily map. In the interest of time, I'm going to skip through some of these quite quickly. In this case study, I wanted to illustrate how the kind of watershed procedures we've just described, admittedly very quickly, but when they're applied to different DEM data sources, they can produce very different results, and so I just wanted to illustrate that. So here we have fairly typical contour data obtained through BC TRIM, so relatively high resolution contour data in BC in an alpine environment. This is a watershed network that's been derived from that. Here we have a fairly typical airborne photogrammetric DEM of the same area, 5-meter ground spacing. And here we have a network associated with that. You'll already notice there's quite a difference between those networks in some areas. And here we have a LiDAR DEM, 1 to 3 meter resolution. Same processing applied to it as the photogrammetric DEM in terms of the DEM generation or the rasterization approach. That's what it looks like, pretty high resolution, lots of detail, and that's what the stream network looks like. And we know just from mapping the landscape and being in there that this is the most realistic, and we would expect it to be anyway. It's the highest quality of the data sources. But I guess what's interesting is when you compare the watershed extents, the LiDAR is blue, photo green, and TRIM red. We'll see the contour-derived watershed is rather erroneous here. The area is very different, the topology is very different because we've got an entire tributary coming in here that we don't see in the photo or in the LiDAR. And then in the difference between the photo and the LiDAR occurs mostly at the upper ends and a little bit at the lower end. And the main reason for these discrepancies is the contouring approach in the BC TRIM data just really doesn't see below trees at all. And the lower reaches of this watershed are all forested. And so what we know from experience is there is a tributary input over here that in the TRIM data is assumed to come in, in the TRIM data it's assumed to come in early, but in reality it comes in late, and so it's outside of the watershed extent that we defined, simply because that data set couldn't see beneath the trees. The photo DEM suffers similar problems in the same area, but not to the same extent, but we see larger discrepancies around the edges in terms of where the ridge lines are defined between the photo and the LiDAR. I could say a lot more about that study, but I just wanted to kind of make a point about the differences between the watersheds and the stream topology with the different methods. This is something that has been implemented in Alberta to quite an extensive degree. I won't say any more about it, but many of you may already be familiar with wet areas mapping. Barry White, I know, has presented on this quite extensively. But it's an approach where you can take the low points in the terrain DEM and infer the water table from a depth to water model, and then transpose that back onto your DEM and get an estimate of water depth across the landscape. So it essentially gives you an index of wetness across the landscape. I'm sure some of you know a lot more about how this works than I do, but it's just one example of how the data have been implemented in an operational way, and Alberta has been one of the leaders in that implementation.